sheaves on projective surfaces and relations to Vafa Witten and Kapustin-Witten invariants for context 3 and 4 folds.
Thank you very much for the introduction. I should thank the organizers for inviting me to this beautiful place. Everyone has been asking me, why am I missing? It's just the place is too beautiful.
Here's the matching result.
There you go. Okay, so I'm giving a report of a series of joint works with, so this is joint, originally it was joint with Gholampur and Shing-Tung Yau. And the work I'm discussing today is joint with Shing-Tung Yau. It's a sequel to the earlier work. So let us start by geometric setup of our project. So let S be a smooth projective surface. Projective surface over C, and with the following cohomology conditions. So I would like H1 of OS to be vanishing, and this let us pick a ample hyperplane class. So let little h be the hyperplane class on this projective surface. So given this information, we are looking at certain moduli space of sheaves. We are defining and computing certain invariants, which I will tell you how they are related to what is called Vafa Witten invariant. So let us fix some choice of a Chern character vector on this. So let's fix a Chern character vector. So these are elements of cohomology theory of S with rational coefficients, R gamma M. And we would like to work with a moduli space of sheaves with this Chern character. So let M H of V denote the moduli space of H semi-stable sheaves on S with Chern character equal to V. We are making an assumption that semi-stability is the same as stability. So stability. And we can also make a further assumption that this moduli space comes with a universal family. So let us assume that M H of V comes with a universal family. For example, if I have the condition that greatest common divisor of R and gamma times the hyperplane class is equal to 1, then that's the condition which is enough for our moduli space to be equal to the universal family. Okay, so we are trying to define invariants, in particular sheaf invariants or Donaldson-Thomas invariants for this moduli space. So in this case, these are just facts which are known for a while now by the work of Richard Thomas and Simon Donaldson. So there is this, so if I have this H times the moduli space, if this is my projection map, then my universal sheaf lives in here, and then there is this object in the derived category, R F tilde. We are looking at trace-free part. This is an object in the derived category of moduli space after pushing forward into here, and it naturally gives us a map to the truncated cotangent complex of our moduli space. And this is what satisfies the conditions of being a perfect deformation obstruction theory. I'm not going into the detail, but anyways, it's kind of like a review. And then this induces a virtual fundamental class over this moduli space, which is the class we will use to integrate against to define the invariants. Okay, so this is a twofold moduli space. It's a surface moduli space. We can construct a certain theory, hybrid theory between twofold and threefold, which kind of is very close to this one. So let us move now one dimension higher. So now let L be a line bundle on S, and X be the total space of this line bundle on S, the non-compact threefold that you can get this way. And I'm going to call this projection map from the line bundle onto the surface Q. Then, of course, fact is the canonical bundle of this threefold is the pullback of L inverse times canonical bundle of the surface. So when the line bundle is the canonical bundle, then X is a non-compact Calabi-Yau threefold. Okay, and the Vafa Witten theory is in fact a theory about this non-compact threefold. Okay, so one thing that I will use later is that, as probably many of you have seen in Hartshorn, so first of all, actually, there is an action of the C star on the fibers of this line bundle. So this dilates this non-compact threefold, first of all. And then this actually tells us, this is in Hartshorn, if I push forward structure sheaf of this non-compact threefold, I will get this module over the symmetric algebra of the fiber. So this is something like this. And you know, the fibers of line bundle are carrying the torus action. So this T in here is basically the character actually that tells us the torus weight of the module that you get downstairs after the module. So this T is a trivial bundle on S with non-trivial C star weight. So with C star weight 1 on the fibers. So if you take the structure sheaf of X, push it forward, you will get a graded module, C star graded module downstairs. Okay, so now, as I said, I'm going to construct a moduli space which is very close to this one. So let us now let co-Cx, which is an abelian subcategory of co of X, be the abelian subcategory of compactly supported sheaves. Sheaves on S. And for this category, for the elements of this category, we can construct a moduli space. So we define a slope function which is the following way. For any element in this compactly supported category, of course minus the zero sheaf, we can define a slope of that sheaf the following way. Okay, so the H slope of a sheaf like E is going to be again first Chern class of the push forward of that sheaf onto the surface, again paired with the hyperplane class divided by the rank of that sheaf after being pushed forward onto the surface. The difference between the moduli space I'm going to talk about and the earlier moduli space is that here our sheaves are just OS modules, but here our sheaves are OX modules, but somehow set theoretically they are supported all on the base. So they include the OS modules and modules over the nilpotent fattening of the base surface S. They are OX modules. Okay, so this gives you a rational number, and that is the definition of a slope for us. Okay, now let mx or mx hv again be the moduli space of mu h semi-stable sheaves. E in this abelian category of compactly supported sheaves on X with Chern character of the push forward of that sheaf to be equal to B. Okay, so I have moduli space of sheaves on this threefold, but I measure everything about these sheaves onto the surface after pushing them forward onto the surface.
Sorry.
Yeah.
The sheets are supported compactly on X or on X?
On X, but X is non-compact, so they cannot be supported on the fibers. I mean, at this point, yeah. It might be you can have some compact variety inside X. I haven't distinguished yet, but essentially they will be all supported on X. Okay, so now again, here we make an assumption that again, if the greatest common divisor of R and gamma times H is equal to 1, mx of HV comes with the universal family. The universal family. Let's call that family again F tilde. Okay. Similar to before, there is an object in the draft category of this moduli space of torsion sheaves on this X, which is E dot, let's call it E dot, and this is defined by work of the Richard Thomas and Daniel Huybrecht. So it's a certain truncation again of Arham, the relative Arham F tilde, together with the shift. And this guy actually again maps onto the cotangent complex of our moduli space. This time the moduli space is moduli space of torsion sheaves on X. So this object in the derived category again induces a virtual fundamental class. So one fact. So if rank, let's say what is, because this is important, so rank of this object is 0 if the line bundle is equal to canonical bundle of the surface, and it is some other number, non-zero number, C1 of L minus omega times H divided by 2 plus 1 if L is not equal to canonical. Actually, yeah, C1 of L times omega. Okay, so rank of this complex determines the degree of the virtual fundamental class. And so if L is equal to omega, virtual dimension of your moduli space is equal to 0. And if not, then you need to be integrating some higher degree class against the virtual cycle to define a number. Okay. So as the construction suggests, this threefold is non-compact, and the moduli space of torsion sheaves on this threefold is also non-compact. And in order to define any invariant, you need to use torus localization. So in order to define invariance, define Donaldson-Thomas invariance, we use the Pandre-Pandey, Graeber, Pandre-Pandey, virtual localization. So our invariants are all given as certain residue integrals that we define with respect to the action of the C star. Okay, so this is what it looks like. So for me, the notation dt hat is this residue dt invariant. So it has dependence on the choice of the Chern character for these sheaves. Has to be fixed to construct the moduli space, and also depends on the whatever class you're integrating, depending on the virtual dimension of this virtual class. You could put 1, or you could put some higher degree class in order to define the variable. So it is given by localization. So it is some class alpha of appropriate degree, and then Euler class of the virtual normal bundle of this dual. This is the virtual normal bundle against the C star fixed virtual class. So what this means is you can see that your deformation obstruction complex also carries a C star action. So you can look at the part of this object in the derived category which is not moving by the torus, and the part that does move by the torus. The virtual normal bundle is given by the Euler class of the part that moves by the torus. And this then is the C star fixed virtual class. So here alpha is an element of C star equivariant cohomology of this modular space with coefficients in Q. And of course, I mean, you localize this class with respect to an equivariant parameter. So localized at equivariant parameter S. Okay, so again, this is in the literature. Okay, so one fact is, so here is a fact, here's a remark. When arithmetic genus of the surface is bigger than 0, our invariants vanish. So the fixed part of this object in the direct category E dot contains a trivial factor. And our dt hat invariants vanish. So for those of you who are not familiar with this part of this construction, if you're doing Gholampur theory, it's a certain phenomenon similar to when you have a K3 surface and you realize that your Gholampur invariants of K3 vanish. Or Donaldson-Thomas invariants of K3 vanish. So when the arithmetic genus of the surface is bigger than 0, this object in the derived category is the one whose cohomologies actually provides you the virtual class. And if there is some trivial bundle in it, there is this first Chern class that appears there, and it just gives you the 0 invariant. The whole thing vanishes. But you can reduce it. So in this case, one can define a certain notion of reduced invariant. I will put it in here, but I'm not sure if actually, but nevertheless, let me put it in here. How we reduce it, we look at, so here is our map. So this is our moduli space. and then there is a map Q that takes us to here, and our universal sheaf lives in here, the deformation obstruction complex also lives in there. So what we can do is we can push forward everything onto the surface and then take that trivial piece out. So we will take this arham, F tilde, it maps onto arham. This is over X times the moduli space. This is over S times the moduli space. And then since the maps are affine maps, they wouldn't have higher cohomologies. So just to push forward, you can put it inside the parentheses because there are no higher cohomologies. So something like that. And then you can define a trace map, and this maps you to structure sheaf of the moduli space. So this composite map gives you a complex. And as you can see, you start from the object whose cohomologies give you the integrand of your integral, as well as via some construction, the base of your integration. And then you can find a way to get it mapped to O, and this is that trivial piece that I was talking about. So if you take the cone of this composite map, this O goes out. So define C dot to be the cone of this. And then here's a theorem, which is with Gholampur and Yau. This was in 2018. We showed that the reduced obstruction theory, the dual of the reduced deformation obstruction complex, is given by a certain truncation of this cone. This was our theory. Okay. And then we proved that this guy is also satisfies the conditions of being a deformation obstruction complex, meaning there is a map from this guy onto the cotangent complex of this moduli space. The idea about these obstruction theories is that you have a certain moduli space, you can put different maps that somewhat approximate the cotangent complex of the moduli space, and these maps can come from different well-defined deformation obstruction complexes with respect to which you can define a notion of integration, and you get different invariants for the same space. So our first one was just the E dot, and via residue integration you define invariants, but of course we can see that the invariants are 0. After reduction you get to here, and then if this guy satisfies certain appropriate cohomology conditions, it also defines invariants, and those invariants are non-zero. So for the same space, you can define different invariants. So it depends on the choice of the suitable obstruction theory. Okay, so now one remark is that what is other benefit of this reduced guy is that the fixed part of reduced the moving part of reduced obstruction complex is the same as moving part of original E dot. This is important because this is basically saying that in order to define non-zero invariance, you calculate the virtual dimension of the modular space, you put an appropriate cohomology class in here, you put the reduced virtual cycle induced by that object in here, and then you need to put something in the denominator, and here construction shows us that the denominator doesn't change. So then we can define the dt reduced the following way, and xh C star virtual reduced, again alpha divided by Euler class of the virtual normal bundle. This is the notion of dt reduced. So these are invariants for this moduli space, but they're 0. Those are also invariants for the same moduli space. All of these are invariants with respect to complex and scalar deformations of the original non-compact threefold. So they are invariants of the deformations of complex and scalar structure. Both of them are invariants for this moduli space. Okay, but somehow these reduced invariants actually have been seen in other places. So let me tell you about Vafa Witten invariants. Vafa Witten invariants. So these are inventions of Yuji Tanaka and Richard Thomas. So what are they? They are invariants. They are invariants associated to a perfect symmetric obstruction theory, obstruction complex for moduli space of Higgs type bundles or Higgs pairs, G and phi. That means I have some pair like this. G is a torsion-free sheaf on S. And together with this Higgs pair, together with something that the authors call the massless condition, which translates mathematically into together with the condition, together with this condition, the trace of this map should be equal to 0. So Yuji Tanaka and Richard Thomas have been looking at the moduli space of certain Higgs pairs on the surface. These come from, in fact, directly from the construction of Vafa and Witten. You're doing some kind of, in the original paper of Vafa and Witten, you have this complex surface, 4-manifold with fixed complex structure. You're doing something like an SU2 gauge theory on this 4-manifold. And they drive certain differential equations. And then these differential equations imply that the solutions to those things are parameterized by certain bundles, or in more generality, torsion-free sheaves on the surface together with the Higgs map. So in some sense, this bundle is the frame bundle associated to the gauge bundle that you have on that surface. So their equations tell you that there is some integrable holomorphic structure on the bundle together with the Higgs map. So this is the algebraic geometric translation of Vafa Witten theory that they came up with. And the idea is that the Vafa Witten moduli space is actually related to this moduli space of torsion sheaves on the threefold. And I will give you an example that you will see how Higgs pairs on the surface relate to sheaves on this threefold. So here is some facts, some remarks. So remark 1 is that Tanaka and Thomas show show that the moduli space of Higgs pairs, so M Higgs on the surface is isomorphic to the moduli space I just defined on the threefold when L is equal to canonical bundle of S. So this is a situation where your X is given by total space of the canonical bundle of S on the surface. So the moduli spaces are equal to each other. The second fact is M Higgs is equipped with a C star action, and which is the same as the C star action on MX HV. Okay. This is important because we have two spaces, but one of them is a non-compactive space, and we have defined invariance for this non-compactive space via the torus localization. So first thing to check is whether the C star loci are compatible with each other, if there is any relation between the two moduli spaces. Okay, so that's the second fact, and then third fact is that over M Higgs S C star, the torus fixed loci of the moduli space, trace of phi, trace of this Higgs map, vanishes automatically. So Tanaka and Thomas are not looking at all the Higgs pairs that we can define on the surface, but they are looking at the ones which have this condition that the trace of phi equal to 0. Massless Higgs pairs, they call it. And over the whole moduli space of Higgs pairs, that's not the case, but over the torus fixed locus, that is the case. Torus fixed Higgs pairs are massless Higgs pairs. And remember that Vafa Witten invariants are invariants of massless Higgs pairs. Okay. So, in fact, C star fixed locus of Tanaka and Thomas is identified with M omega MXH nu C star. Okay, now you have two spaces which are absolutely identical to each other. Does it imply that your invariants are equal? That's not the case, because again, the notion of invariant depends on the obstruction theory that you put there, depends on the integrand that you put there. So you should also show that whatever ingredients they use to define the invariants are the same. So here's fact 4. The fixed part of E dot Tanaka Thomas, the obstruction complex for this Higgs pair moduli space, is equivalent in K theory, that is, in K theory, to the E dot reduced that I just defined, to the fixed part of E dot reduced. So this fact implies that the virtual cycle that Tanaka and Thomas obtained via this machinery of Behrend and Fontecchi, for example, is the same as the virtual cycle of us. And now, this part remains. So this part is the same. The moduli spaces are identical. The torus fixed loci are identical. Cycles are identical. Now this part. And E dot Tanaka-Thomas moving is differ from E dot moving by a trivial bundle of rank exactly arithmetic genus of the surface. So in order to define our invariance, we take this piece out. So this is actually telling us that, okay, if I use my E dot reduced, Tanaka-Thomas invariants are exactly equal to the deformation invariance that we defined. So this implies that Tanaka-Thomas invariants are equal to the dt hat reduced that we just defined. Okay, so in fact, this dt hat for x, as you remember, it depended on the choice of Chern character and the class alpha. When line bundle is equal to the canonical bundle, virtual dimension of the moduli space is equal to 0. So that means that I'm integrating only 1 via residue integration. And this is equal to the Vafa Witten invariance for the same choice of Chern character up to some equivariant parameter. Okay, so in our work with Gholampur and Yau, we were trying to define some notion of invariance for torsion sheaves on the non-compact threefold, and somehow the lucky situation was that we realized our moduli spaces are identical, torus fixed loci are identical, torus fixed part of obstruction complex are identical, moving parts, as soon as we reduced one of the obstruction theories, are identical, so our invariants are identical. And the objects in the draft category that they use is kind of very different from the one that we use. Okay. So yeah, so we just got lucky and our invariants kind of matched with theirs. Now, one important feature of Vafa Witten invariance is that there's a conjecture by Vafa and Witten, and actually many other physicists, that the partition function of Vafa Witten invariants are given by modular forms. So this is a very interesting feature for those in enumerative geometry, because you can obtain full partition function from these things.
Can you say more about the types of modular forms that is expected?
I will show you some. They are like Cuscutal forms, some of them. Cuscutal forms. Yeah, they are given by product of eta functions, for instance. So I told you that I will relate sheaves on this threefold to the Higgs pairs, at least one concrete example so that everyone has a picture. So let's talk about torus fixed loci. Torus fixed loci of M X H nu, which is the same as M Higgs torus C star fixed, yeah, M Higgs of Tanaka-Thomas. We are looking at a non-compact threefold. There's a torus acting on this thing, and our torus equivariant sheaves or torus fixed sheaves at least have the property that their support shouldn't move by the torus. So they are supported either on this base surface, because the torus is dilating the fibers of this line bundle, or they're supported on some nilpotent fattening of the base surface. So let's make one example. Let's go one dimension lower and think about the twofolds. Let's say I have a twofold. I have this line bundle over this complex line. Okay, so this is the analog of my S. And let's say locally, I would like to look at my sheaves locally. So let's say this is the y-axis and this is the x-axis. And I can look at certain sheaves whose support doesn't move. So there is this C star dilating the fibers of this guy. And I need to look at sheaves which are supported on the base, because the base is not moving by the torus. So okay, one of those is, for instance, structure sheaf of the surface. This certainly doesn't move with the torus. So what is this locally? Locally, this is given by polynomials in x and y variable divided by ideal of this base in this non-compact threefold. Okay, so that's the ideal of y. So this is locally identified with C of x. So our sheaves could look like this. And then they could also be supported scheme theoretically on a nilpotent fattening of the base surface. So for example, I can look at structure sheaf of double the surface. So that again locally is something like polynomials in x and y divided by y squared. Okay, so that is something like C of x, direct sum C of x times y. These are the only things that survive. So this is what you will get. And you can keep going. So when you look at objects like this, which are rank 1 and supported on this nilpotent fattening of the surface, you also get a coaction by the fibers. And that's basically your Higgs map. So one thing that you can do, you can take this and multiply it by y. So you will get C of x times y. But you can multiply by y. This is the same as tensoring with the line bundle. So you will get C of x times y plus C of x times y squared. But everything is a module in here, so that vanishes. Okay, so this gives you a 2 by 2 matrix. So the first guy goes to the second guy, and this one goes to 0. And in fact, this is given by multiplication by y. So this is your Higgs field. This is your map field. So as you can see, you start from a sheaf, which is torsion. It is supported on codimension 1, and you will get some kind of a Higgs pair over there. Now, everywhere that you see a y, the y experiences the action of the torus. So this is also automatically telling you that you will get a graded module when you push forward. So if I call this thing E0, and if I call this module E1, there is no y in here, so this sits in degree 0 piece, and there is a y in here, this sits in degree 1 piece of this C star graded module. So this is degree 0, degree 1, E0, E1. And then what is this? This is nothing but E0 tensor with line bundle. This is E1 tensor with the line bundle. Okay, how about the torus fixed loci? If you start from a torus fixed sheaf, which is a sheaf like how I started with, O of 2s is a such sheaf, then the complex, then the Higgs pair that you get down there also needs to be torus fixed. Obviously, torus is moving guys in here because there's a y in here, and torus is also moving guys in here. The only way that this pair could be torus fixed is that same graded module goes to the same grade, so the same weighted spaces get mapped to each other. The only pieces that have that property, this is degree 0, this is actually shifts, the degree shifts when you tensor with line bundle, 1 and 2. The only two fixed parts are basically this. So the fixed part of this Higgs pair is in fact isomorphic to E1 going to E0 times L. E1 is this guy, E0 times L is that guy. So the torus fixed loci of Higgs pair moduli space give you maps between sheaves, and these are our flags. Now in this example, over S, this is rank 1 module, and this is a rank 1 module. Let's go up in dimension 1. So you have rank 1 objects. So this is rank 1 over S, and this is rank 1 over S. So if you have a smooth projective surface and you have rank 1 torsion-free sheaves on it, these are basically ideal sheaves, or twists of ideal sheaves. So in this case, when rank of E0 equal to E1 equal to 1, then E0 is some ideal sheaf of n1 many points may be twisted by some divisor, and E1 is also ideal sheaf of some n2 many points twisted by some other divisor. And so this is telling you that the torus fixed loci of your Higgs pair moduli space are given by flags of twisted ideal sheaves. So you have I1 twisted by D1 goes to I2 twisted by D2, together with this twisting by L, which comes from the threefold. You can also put the twist all on one side. Okay. So as these are ideal sheaves, what this represents, this is actually represents, I mean, there is some stability actually. Stability, also I should say, stability implies that in this case, this map phi is injective. Let's call this map phi prime or phi C star. After all, it is the map phi we obtain after looking at only torus fixed part of our Higgs pair. So it looks like we are looking at nesting of ideal sheaves of points and curves on this surface. So the picture for this thing is configurations of one-dimensional subschemes sitting inside each other. This is subscheme 1, Z2, AB, and Z1. And this is what we called in work with Yau nested Hilbert scheme. Okay, so when you look at the torus fixed locus of the moduli space of either Higgs pairs, massless Higgs pairs, or torsion sheaves on this non-compact threefold, there is a component, connected component that parameterizes nested configurations of 1 and 0 dimensional subschemes of this surface. So a part of contributions to the Vafa Witten invariance come from partition functions of invariance of nested Hilbert scheme. Okay. How much time do I have? How much? 2 minutes? 12 minutes. Okay. Okay. So, in this case, I looked at the situation where I cooked up an example where I start from a sheaf like this, and then you looked at even the modules, and you will see that over their support, the modules after pushing forward are rank 1. That's not always the case. In general, if we start from some E in this category of compactly supported sheaves, such that E is an element of our moduli space, torus fixed locus of our moduli space. So this Chern character this was, by the way, as you remember, this was by definition the Chern character of the push forward of our sheaf. This was given by R gamma n. In general, after you're pushing forward your sheaf, you will get some sum of modules exactly like that. And each module has rank, let's say rank Ri, and the sum of the ranks, of course, will be the rank of the original sheaf over its support. So this is actually telling you that the torus fixed loci of the moduli space are somehow partitioned by the rank of the sheaf that you start with. So the torus fixed loci of this moduli space is given by the first partition, which is the partition R, MR. Then the second partition, which is the partition of flags E1 plus E2s, where this guy has rank 1 and this one has rank R minus 1. So this is this partition. And it keeps going. And originally, essentially, you hit this 1, 1, 1 partition R many times. This is the one that, in this case of rank 2, we called nested Hilbert scheme. In the language of physics, physicists have been calling this instanton moduli space, instanton branch. Algebra-geometrically, these are moduli spaces of sheaves of rank R on the surface, no Higgs field. And the rest, somehow wrongly, are known as monopole branch, but wrongly. For instance, I asked, Vafa, for instance, was telling me, you guys should stop calling this the monopole branch. Monopole means something else. So I'm not sure. So I think also Thomas and Tanaka somewhere pointed out that probably this name monopole branch is wrong. So anyways. So everything that you see in here is configurations of E1 plus E2, some number of EIs such that the rank adds up to R, and together with non-trivial Higgs field. And only guys in here they don't have the Higgs field. Okay. So now some results. Okay, so here's the theorem. When R is equal to 2, the only possible partitions are the instanton branch together with the twofold nested Hilbert scheme. I have a completely calculated partition deformation obstruction theory of these guys. So this actually, DT invariants in this case are going to be, so this one induces Wafa-Witten invariance together with certain combinatorial coefficients. So this is via some wall crossing, actually, which is developed by Mochizuki, Takuro Mochizuki, who actually works in the same institute as the other Mochizuki. And this one is actually, you can see some of our calculations in our work with Gholampur and Yau. So some of the things that we try to verify is that, for instance, first of all, maybe remark, when S is Fano or K3, the monopole branch, let's call it again, monopole branch, meaning the union of all these guys, which have the non-trivial Higgs field, is equal to, actually vanishes, is empty. So if you want to have hope for proving the Vafa Witten theory, you need to look at partition functions of the instanton branch and prove modularity right there, because these invariants actually vanish. So this is important because partition functions of Wafa-Witten invariants are not supposed to, I don't think there is any result that they're given by modular forms, but some combinatorial modification of them are, because they are equal to the left-hand side. So this was important result. Also, there are some examples. For example, if S is quintic surface in quintic in P3, or some complete intersection of type 2,2 in P4, and there are some more examples that we calculated. If these are the cases, then you can actually use some argument, and you will see that this part of this, twisting by this divisor, these divisors cancel each other. And so in the rank 2 case, where the original rank is equal to 2, this guy, M11, is given by nested Hilbert scheme of only points. So in this case, in these cases, M11 is the twofold nested Hilbert scheme of points. And we in fact calculated partition functions of these things, so we showed that they are given by modular forms. In order to do this calculation, we actually didn't need to work hard because Carlson and Okunkov had written a paper on defining vertex operators for Hilbert scheme of points. And staring at their integrals, you can actually see that using their integrals, not only you can define some partition function for Hilbert scheme of points, you can also define a partition function for the nested Hilbert scheme of points. So all we needed to do was to learn the calculus of vertex operators defined by Carlson and Okunkov. So using results of Carlson and Okunkov, we obtained modular forms. Okay, so there are these cases where this guy is non-empty, left-hand side is conjectural to be actually modular, and then this one is also modular by this result. Those are these cases where your surface is something like this, and your threefold is given by canonical bundle of the surface. Okay. So how about hard rank now? So what if R is bigger than 2? Okay, in that case, in fact, I should say that, okay, so in that case, you have again this decomposition in terms of partitions of the rank. So you have this guy. And two of the people who have been having most progress over this locus are Goche and Kuhl. So the partition function of the instanton branch, I mean, Goche and Kuhl have verified lots of interesting properties on this one. And then, so this is for R bigger than 2. And then this part actually is given by the nested Hilbert scheme. It's not so hard. So this is the theory that we developed. And then the remaining parts are whatever that is lying in here. So those components are components. So this M, C star minus MR union M11 is parameterizing flags of higher rank sheaves. Maybe something like this, where rank of EIs could be all bigger or equal to 1. And okay, so there are certain technicalities. If you want to define a notion of deformation obstruction theory for these things, I don't have time. But the certain technicality is that, first of all, you need to have the condition that these maps are injective, or else you will never, ever obtain a well-defined perfect deformation obstruction theory. So we need phi1, phi2, phi n minus 1. We need phi i's to be injective. The reason for that is that there is some complex E dot. I will put it in here. It's the sum of Arham EI. It's the cone between the two things. So cone between this and the sum from 1 to n minus 1, Arham EI minus 1 EI. This complex, okay, so this is not so hard. Imagine that you have only two sheaves in here, and you would like to obtain some object whose cohomologies gives you deformations of E1 to E2 or obstructions. What would you do? Illuzi tells you, deform the first sheaf, deform the second sheaf, and deform the map, and look at the difference. Deformation of the first sheaf is Arham E1, E1, plus Arham E2, E2. Then deformation of the map is morphisms from E1 to E2, and then you subtract it. Take the call. It's very easy. This is always the case, actually. You have whatever flag, this object gives you the deformation obstruction theory. The problem is that whether this thing is actually perfect or not. It's supposed to have cohomologies only in degree -1 and 0. If the maps phi's are not injective, in fact, it will have a term in degree -2. And that degree -2 term is exactly given by the kernel of the phi. So here's an example. Some example, let's say I'm looking at E1 to E2. If phi is not injective, E dot will be will have an amplitude -2 to 0, where the -2 term has contributions from kernel of phi. So this is what prevents you to actually construct a well-defined notion of deformation obstruction theory, even for twofold flags. When these are ideal sheaves, rank 1, there is no problem. The map is supposed to be either isomorphism, which is not, because these have different Chern characters, or an injection, or the zero map. This doesn't happen. But if these have higher ranks, then you run into this problem. So you cannot define a notion of invariant for this moduli space. So in order to remedy this situation, we are looking at a moduli space of these flags with a certain stability condition. So we call this thing moduli space of high rank flags equipped with Schmitt stability condition. So those of you who have been working on moduli space of vector bundles on curves, probably you remember these Bradlow pairs and Bradlow triples and things like that. So these are just very similar, except their support is a surface. And if you look at their work, you will see that there is a notion of Schmitt stability for quivers. So Schmitt stability is some stability that you define for quivers. So if you have a quiver like this, you put in torsion-free sheaves on it, like that. Schmitt stability condition comes with parameters, as many parameters as there are the vertices of your AN quiver. So if you have n vertices, Schmitt stability condition comes with n parameters. So our realization was that when we set QIs all equal to each other, and let the QI to go to be asymptotically large, and let equal to Q, and let Q become asymptotically large, then we can prove that let's call this some quiver Q dot satisfies the condition that phi i's will be all injective. So for these certain quivers of flags on this complex surface, equipped with this Schmitt stability condition, when we let the parameter of the stability become asymptotically large, we actually constructed a deformation obstruction theory. And then the question is, how can we show that this contributes to Vafa Witten invariance? So this is the last bit that I put in here. We also showed, so this is work with Yau and myself. This is 2019. Yeah, the paper was put in arXiv several months ago. We showed that for a certain critical value of Q, let's call it Q critical, slope stability of E C star fixed sheaf in category of compactly supported sheaves on X minus 0 sheaves implies Q critical stability of the high rank flag of Q dot. So all we need to do is that somehow this is a wrong picture because these Q's, I didn't tell you what they are. These are actually polynomials. Everything is for calculation of the slopes. We need to look at the Hilbert polynomials. So these are polynomials, but we are looking at their leading coefficients. And so imagine that you have some moduli space of stability conditions, and we have this range. So here is Q critical, where we have the Vafa Witten invariance, because our DT invariants of torsion sheaves on the threefold are Vafa Witten invariants. So these slope stable sheaves in this category are Q critical quivers that we obtain after projection and taking the torus fixed locus, for which we don't have any well-defined obstruction theory. And then there is this corner of this manifold of stability conditions, which is Q asymptotically large corner, for which we have invariance. And we have well-defined obstruction theory. So in order to compute all the contributions of the rest of the components of the monopole branch, what is actually in here, to Vafa Witten invariance, you need to actually wall cross the quiver moduli space by perturbing the stability condition from Q asymptotically large to this Q critical, which we have computed in the paper. This wall crossing is different from, by the way, wall crossing defined by Kontsevich and Soibelman. It's not motific. It's the wall crossing of the virtual classes. So this wall crossing is the wall crossing in the master space. Also proposed, if you like, by Mochizuki. Certain wall crossing that relates virtual classes to each other. And this is our work in progress. So work in progress with my recent postdoc with Michael McGreen, whose work probably came up in the talk of Bezrukovnikov yesterday. So yeah, so we are kind of right now in this stage, and I stop here.